All right, so 11.6, we are going to talk about cylinders and surfaces. Now, before we even get going, I want to talk about the difference between these two things so you know what's going on. Number one thing, your cylinders are not going to look like typical just cylinders. They're not going to look all like soda cans. What a cylinder means in 3 dimensions is the following. What a cylinder is some curve that can be traced on a plane that is projected along an axis. And along that axis, the curve does not change. So if I have a parabola, and I say, hey, here's a parabola on a plane, and I take that parabola and I just project it straight. That is what a cylinder is considered to be in 3D. It's this trace, we call it a trace, something to be drawn on a plane. The trace does not change as we're moving along what's called the direction axis or directrix. That's what a cylinder is. What a surface is this thing that still can be traced, but as I move along the directrix, the direction axis, it changes. It can get bigger, smaller, it can change, and that gives us this thing that's a surface or this thing that's a cylinder. Do you guys see the difference? One changes in 3D, one only changes, one doesn't change in 3D. One is a shape that just keeps on going. And so that's what we're going to talk about. We'll talk about cylinders first. I'm going to tell you exactly how to tell whether an equation is a cylinder or a surface and exactly how to tell what type of surface it is. I'll tell you right now, cylinders are a whole lot easier than surfaces are. So we'll talk about those first, you get a hang of it, and then we're going to progress. So number one thing, let's talk about cylinders. First thing, and here's the whole point of what makes a cylinder a cylinder. If you have an equation with 2 variables, how many axes do we have in 3D? 3. If we have an equation with 2 variables, then only 2 variables can be changing. The other one would be constant. So that means that right there, just having the fact of 2 variables is going to dictate whether we have an equation that is a cylinder or a surface. So how many variables do cylinders have?
2.
How many variables do surfaces have?
3.
That right there tells you what you're dealing with. All right. So firstly, equations of cylinders have only 2 variables. What these equations are going to do for you. These equations are going to give you a trace. Remember talking about the traces? The trace is the shape, just like the shape on a plane. So what these equations are going to do are give you a trace on the plane that those variables tell you. So if you have an x and a y, your trace is going to be on the xy plane. If you have x and a z, your trace is going to be on the xz plane. If you have a y and a z, your trace is going to be on the yz plane. So these equations will give you a trace of the curve on whatever plane is denoted by the given variables. How many variables am I going to give you for cylinders?
2.
Planes each have 2 variables, x, y, yz, xz. Do you guys get the picture of that? Well, you will. We'll literally get some pictures. So these equations give a trace of the curve on whatever coordinate plane is denoted by the variables given. That sounds a lot more wordy, a lot harder than it is. It's really not, just the best way I can think of to describe that. Also, one more thing. Man, I'm just really praying you guys know this. Do you know anything about conic sections? Conic sections like circles, ellipses, hyperbolas, and parabolas. Oh my goodness, if you know those equations, this is going to be so nice. Also, I have to tell you this right now. this stuff, it seems like, oh, it's only one section. You've never taken Calc 3, most of you, before. Some of you, you know what I'm about to say. This section, the idea of surfaces and cylinders and what we do with them, I'm not even joking you, we use that in every chapter that we get, every single one of them. So we talk about graphing in chapter 12, these things. Actually, we talk about functions on these surfaces. Crazy. We use it in chapter 13, we use it in chapter 14, we use it in chapter 15, we use it in every single chapter that we get. So I'm going to try to crush this here real quick, not real quick, but I'm going to also make sure that you understand it, because this is a big deal. Please don't gloss this over, like, I really don't get conic sections. If you don't, I got some videos from Math C, Intermediate Algebra, you click on those things, you watch chapter 13, 13.1, 13.2, it will tell you everything that you will need to know about conic sections and what to do with them. Is that clear for you? That would be in your best interest, trust me, because if a lot of the stuff we're doing today is like, watch those sections and like, oh, that's an ellipse. That's a hyperbolic. That's what we're talking about. That's a big deal. So anyway, equation cylinders got two variables. Those variables tell you what plane your trace is going to be on. Number 2. The curve is always going to be directed along the axis of the missing variable. If we have a trace on a plane xy, then it can only project one way, along the z, along the missing variable. So the curve is always directed along the axis of the missing variable. Number 3, I've already mentioned it, but I'm going to write it down. The curve or the trace for cylinders does not change along that direction axis, along the directrix, along the axis of the missing variable. And lastly, I'm not going to write it down. Just keep this in mind. These things aren't all going to look like soda cans or toilet paper rolls, all right? They're going to be just a shape that's not changing along an axis. That is what a cylinder is in Calculus 3. Head nod if you're okay with the ideas here. So let me test you real quick. I'm going to put an example up on the board. We're going to go through it, but just basically think of it this way. Basically, it's a curve that we are projecting into 3D along an axis. Curve don't change. So we take this curve that we draw and just shoot it out there. Just pass it out there through space along an axis. That's the idea. So if you feel okay with it for real. All right. So let me test you here real quick. We're going to do... do that one. Z equals 4 minus x squared. Now, I'm going to give you a piece of advice when you're doing these. It seems like almost pedantic, like, oh, why are we doing this? But write down everything that you know about this. Trust me, it's going to help you, especially when we get to surfaces. That's a big deal. So what I mean by write down everything that we know about it. Well, firstly, count the variables. How many variables do you see?
2.
What's that mean? A surface or a cylinder? And actually, we're not in surfaces yet, but this is the way I want you to think. I'm modeling how my thought process goes. How many variables do we got?
2.
That means we have a
cylinder.
Write it down. Two variables means we got a cylinder, for sure. Write down where the trace is going to be. The trace is just the picture of the curve. So the trace, write down the axis that the trace is going to be drawn on. The trace is always drawn on the axis, the plane. I misspoke there. Write down the trace of write down the plane that the trace is going to be drawn on. The plane is always given by the variables that you are given. There's nothing tricky about this. So what variables do you have again?
X and Z.
So this trace, the picture of the curve, is going to be on the XZ plane. The picture is drawn on a plane. I misspoke, and I'm sorry, I want to clarify that. The trace is drawn on the plane. The plane is given by the variables that you are given. So if I'm given XZ, that trace is going to be on the XZ plane. Does that make sense to you? How can it be otherwise? You don't even have a Y variable. You can't you can't do anything on the Y plane. That's literally why it doesn't change along the way. And lastly, I want you to write what axis it's going along, traveling along, directed along, the directrix, the axis of travel, whatever you want to call that, I really don't care, but where it's being projected. It's always being projected along the axis of the missing variable. Hey, what variable is missing?
Y.
So this is directed along the y-axis. So, how we draw the first ever 3D picture you guys have probably ever drawn of cylinders or surfaces. It's not super hard if you follow the directions I'm going to tell you, okay? Number one thing I want to do, I want to solve for the trace. So, when we solve for the trace, I do things like, okay, that looks okay to me, but this looks a little bit better. Because what I'm trying to do is change this into some sort of conic section. A lot of these are going to be conic sections. And I know what that one means. What this means, and write down everything, what this means is, this is a, do you know what shape that is? If you know anything about parabola. Is this opening upward or downward?
Downward.
Downward, and I'm going to specify that a little better, okay? It's opening towards the negative part of whatever axis. Also, that plus 4 does something. Shifts it up. Along what axis? Not the y. That's right. Now we have 3 axes, and with cylinders, they're taken 2 at a time. So this is on the XZ plane, and it's shifted up 4 on the Z axis. Does that make sense to you? That's what I want to have you think like. It's weird. So everything we know is it's a parabola. It's shifted up 4 on the Z axis. And it's open. I'm not going to say opening downward because when we get like the sideways stuff, that doesn't really make a whole lot of sense. So I'm going to say it's opening towards the negative z-axis. And we're about ready to draw it. Uh-oh, just got real. I got serious. Please draw a right-hand three-dimensional coordinate system for me all the time with an X and a Y and a Z just like this. So here's the deal. Number one thing, you have to understand what plane you are on. Everyone in class, what plane are we on right now? XZ, that's the one we're on. Draw the picture of your parabola on that plane. That's what the trace is for. It says, hey, draw your picture first. So we say, we're a cylinder, of course. The trace is on that plane. So on this plane, XZ plane, we're going to draw a picture of this parabola that is shifted up 4, watch carefully, shifted up 4 on the z-axis. Do you get the picture? It's opening,
No.
Yeah.
Yeah.
It's opening this way towards the negative z-axis. That's why we don't say open up or downward, because on along the x and y, it's a little weird to think like that. So opening towards the negative z-axis. So it's going this way. Okay? Where's it going to cross? Just imagine the y not even being there right now, okay? Where's it going to cross the x axis?
2, -2.
How would you figure out 2, -2? Oh my gosh, it's a parabola. We can do things like if z equals 0, x is plus or minus 2, just a little math word, but if z is 0, don't even consider the y for the trace. Just consider the plane for the trace. If z is 0, I know I'm crossing here and here. I'd like to know if you feel okay on finding these points at least. You see where the +4 on the z-axis, it's a parabola. If you're not, go watch those videos, get familiar with shifts, things like that. Also in chapter 8 of that same class, Intermediate Algebra Math C, I talk about shifting and what these things actually do. And chapter 11, we talk specifically about quadratics, so maybe worth your time. The parabolas are going to look funny because this is not on the board facing you, it's like into the board. So this parabola is going to do this. I'm going to draw it in purple here. A little funky because it's going backwards. It's not going to be this, it's not going to look symmetrical because it's going away from you. Does that make sense to you? Now, the next thing, I want to make sure you're all with me here. We've got parabola. It's on the xz plane. It's shifted up 4 spots, open towards the negative z-axis. I know it crosses -2 and 2 because I set the z equal to 0, and I can solve for my x-intercepts. Now, what axis is it directed along?
Y.
Because I asked you. Sorry. Whatever, I know this is horrible. Whatever axis it's directed along, draw lines parallel to that axis, whatever it is, that go through the important points, like this. Yeah? Parallel?
No.
What axis?
It's Y.
Yeah. Pretty good. And then what we're going to do is, this just gives us some idea, some concept of it spreading out along the y. Just redraw your shape a couple times. And you get this picture, hopefully you see the picture. Do you guys see the picture I'm trying to draw here? You get this picture of this parabola traversing along the y-axis into space. Is the parabola changing along the y-axis? There's no y variable. It cannot vary along the y-axis. That's the idea. Oh my gosh, I'm putting you to sleep. Goodness, I didn't think I was that boring. I could be boringer. It's a word too. It traverses along the y-axis. I'm probably describing some professors out there. Sorry, professors. Anyway. So this is the idea. This is the idea of a cylinder. A cylinder is one picture directed along an axis. We spent a lot of time on this one. We're going to move pretty fast through some of the other ones. Why? Because they all work like this. Number of variables, find the trace on the appropriate plane, and then direct it along an axis. Did this make sense? Show of hands if it does make sense. Question?
Is there a reason why you didn't put arrows?
Down here?
Yeah, like on.
It's a lazy man. Dotted arrows. And then it's going this way, so we can even shade it if we want. That looks worse though, so thanks for ruining it. Just kidding, just kidding. I can't undo that. If this school would only give me a computer that actually works and allows me to graph these things on computer. But I tell you, I want a smart board for this, right? Y'all get together and get me a smart board. We can do this in 3D and make it, just put on glasses, but boom, be inside the cylinder. Awesome. Let's keep going, shall we? There we go. 9x squared plus 9y squared equals 36. Right now, everyone in class, what are we dealing with, a surface or a cylinder? Technically, they're all surfaces, but specifically, it's a special class of surfaces called a cylinder. Why? How many variables we got? 2 variables. Write it down. So 2 variables. Cylinder. Tell me, what trace, right side only, what trace is the picture of this thing going to be on? What plane? What plane is the trace going to be on? XY. XY can't be an axis, okay. XY plane, that makes sense. Tell me, what axis, it's supposed to be an arrow, what axis is this figure, whatever it is, going to be projected along, directed along?
Z.
Make sure you follow those things when we're drawing our picture right now. Okay, well, here we did the same thing. We solved for a picture that actually looked nice. We were able to identify it. I knew parabola. Shifted up 4 spots, heading towards a negative z-axis. That's fantastic. Here we go. Okay, this looks pretty familiar to me. Do you know what shape that is? Yeah, it's not a circle. It'd be a circle if that was also a 9 or if that was also 4, but it's not. So let's try to put these things in standard form. That way we have a good idea what they look like. So in this case, I would divide by 36 to get that 1. Some of you are wishing right now that you knew a little bit more about conic sections. Here's the deal. If you know that's an ellipse, and you know it's on what plane? XY. Well, if you knew that, you could tell me what, so this is, with intercepts of, if you knew that it was an ellipse and you knew it's on the XY plane, then you should be able to tell me the intercepts of what those things are, how far it spreads out. What are the, for those of you who know, the x-intercepts of that ellipse?
2 and -2.
How do you find out the 2 and the -2? Do you remember? Look underneath the x. Oh, that's the variable. What number is that?
4.
Take the square root. Those are always your x-intercepts every single time. Just don't forget the plus and minus because ellipses spread out both directions. With that being said, everyone, y-intercepts right now. How about z-intercepts? Oops. There is none because it's traveling along the z-axis. Isn't that kind of cool? That you can't even get them. They don't exist. So here's what we're going to do. We're going to draw it same exact way we did. Don't put the figure on the wrong plane. This figure has to be on the what plane? And if you know about ellipses, then you know all I have to do on that plane is mark out the intercepts on the x-axis, mark out the intercepts on the y-axis, and connect them with a circle-looking thing, or like a Stewie head. That's what mine turned out to be anyway. So right now, I know ellipse on the xy plane. Why? It's the only variables I was given. I know that because I put it in standard form for ellipses, my x-intercepts are 2 and -2. Y-intercepts are 3 and -3. I know it's an ellipse. I'm going to try to draw this as well as I can. good as I got. Just a little bit. And then we reread the stuff. We go, okay, do we have an ellipse?
Yes.
Is it on the XY plane?
Yes.
Do our intercepts match up with what we want?
Yes.
What axis is it directed along?
Or
So
Z.
at the important points, I'm just going to pick these ones. At the important points, I'm going to make some vertical lines going up because I want these direction axes to be parallel to the Z. If you are using pencil, which I am not, you can make these a little bit lighter and it looks a lot better. All right, so just really light lines make this look better. And then we're going to draw, hopefully, the same looking ellipse along all of this stuff. Or we'll draw at least like 2 of them, okay, so we get a good picture of what's happening. It's not going to be perfect, but you get the picture of that cylinder now traversing along the z-axis. It's not changing. Show of hands, feel okay with that one? Okay, is it making sense to you?
Yeah.
Do you feel like you could do some of this stuff?
Yes.
Let's try one more together. I'll give you about one on your own. We'll talk about one more, and then we're done with cylinders. We'll talk about surfaces in general. Can you tell me if any of this following information needs to change based on what I've just given you? Does the first thing need to change?
No.
Cylinder? For sure.
Yes.
Is the trace still on the XZ plane?
No.
What's the trace on?
Why?
Is it directed along the Y-axis still?
No.
What's it directed along?
X-axis.
Oh my gosh, what does it look like? I don't know. That's why we solve these things to look like conic sections or functions that we understand. So me personally, I would make this in terms of y, so I would solve for z, because I like drawing on the z as my up and down axis. That makes a little more sense to me. So I would solve this for z equals 1 over y. Oh my gosh, we got my favorite dance move of all time. Remember the y equals 1 over x? You know that one? It's like, what? What? For me? For you? For me? For you? That's how we dance. That's how we do it. And we get the absolute value function. What? No, you don't believe me? You're looking at me like I'm an idiot. Why? I don't even understand. Okay. So I got my dance moves from So You Think You Can Dance. Whatever. Oh no, what's the game? That's not So You Think.
Just stay.
Dance Dance Revolution.
Oh.
Do you see why we might want to pick Z to be first? Because if I'm going to draw this, the ZY plane becomes the picture of the XY plane. Z becomes the Y, Y becomes the X. It's easy to graph like that. So let's go ahead and draw this thing. I don't have a whole lot to say about what this is because it's not a conic section. It's the favorite dance move graph. It's like 1 over X, it's 1 over Y now. It's the same idea. picture. If you know about that z equals 1 over y, it's mutually asymptotic. It means we have an asymptote along the z. We also have one along the y. Right now, I want you to imagine the x-axis isn't even there. We just have, we don't even have it. Let's just draw the picture of this, and it should look just like that. Just a regular, nice looking curve. But then there's also one down here. Are you guys okay on the z equals 1 over y? So solve it for a variable. If it's a conic section, you made out, that's great. If not, well, at least you'll have a function. Doesn't matter what the function is. Draw a picture of that function. And then we go, well, okay. That's practically it. What axis is this directed along? At the x-axis. This is the one that kind of gets people. This is why we're doing this particular example. A lot of people still don't understand how the x-axis works. The x-axis right now doesn't come straight out at you. It's weird, but the x-axis is not parallel to the z. That is not what's happening. The x-axis, make your lines parallel to the x-axis. If it's along the x-axis is diagonal, so I'm going to make them parallel. There's no really good points. It doesn't really matter all that much. What this thing is doing is projecting along this axis. We just give it these lines to make it show where it's headed. It gives it a better image. You guys see the image I'm trying to get out of it. If we draw at least one more, so same shape. Messed it up. Then what we're talking about is this surface of the cylinder traveling this way. And the one down there. That doesn't look that great to me, but can you get the picture of what I'm trying to do here? It's like a skateboard ramp going this way, and a reverse skateboard ramp going this way. It's coming out at you. That's what's happening. For real, show of hands if you're okay with what I'm talking about. Okay, good. Can you do it?
Yes.
Find the plane, draw the picture on the plane, draw some lines that are parallel to whatever axis it's directed along, and just redraw the picture. Don't change the picture, because if there's no variable for the axis that we're given, it doesn't change along the axis. Just keep on redrawing. That's the idea. Question?
Is the, within the curve, is that solid, or the outside of the curve is solid?
The curve itself is like the thinnest piece of paper, ever. So this is like a toilet paper roll with you couldn't even use it to wipe. It's like it's like a soda can. All right, just the soda can with no top, no bottom, going forever, and it's ultra thin.
Okay.
And this is like a skateboard ramp that has no width to it. Basically no dimension.
We couldn't skateboard. Gotcha.
You had
could try it.
an imaginary skateboard, maybe? Yeah, it's not solid.
Okay.
It's not solid.
Okay.
Is it making sense, though? This one, especially, because it looks kind of weird. That's a cylinder. That's a cylinder in 3D. That's what it is. We're not going to do this one. I just want to ask you about it. That one, kind of weird. What shape is that in 3D? Let me give you a little hint. If you can draw it in 2D, then it is a cylinder in 3D, because the 2D shape doesn't change. I can draw that in 2D. Yep. I can draw that in 2D. Yes, I can. I can draw them in 2D. Then that's a cylinder in 3D, just projected. So what is that? Surface, cylinder.
Cylinder.
Technically surface, but we call it a cylinder because it doesn't change along what axis?
X.
So we would draw this one by just a regular old cosine curve, and then project it this way. It'd be a nice, ocean wave going along, this way, but projected out. That's how that thing would look. Isn't that kind of neat? That's the idea here, folks. If I give you like one of these on a test, could you do it?
Yes.
On a what now? We have tests in here? It's not like a math class or anything. Here's the issue. When we get to something called vector functions, what vector functions do is they start putting curves on this, spiraling up. They put curves on this, traversing the skateboard ramp. They do that sort of thing. They put curves on this, traversing the curve. If you do not know how to draw the cylinders, there is no way that you're going to draw that curve. Does that make sense to you? So I gotta have you know this, not just because I'm saying, hey, draw a cylinder. Yeah, you can draw a cylinder, it's pretty easy. But then I'm gonna say, if you can draw the cylinder, let's put some curves on that cylinder. And then that gets kind of crazy if you don't know how to draw a cylinder. So does it really make sense?
Yes.
Do you have any questions on this? Could you at least tell me what plane the trace is on at any time? Could you tell me what axis it's directed along?
Yes.
At least that's a start. All right, it's going to take a little bit of practice. Right now, we're going to switch gears a little bit and say, okay, all right, what if we don't just have two variables? If we don't just have two variables, then there's more than two variables that can change. If there's three variables that can change, not only does the two variables give us a curve, but then that curve the shape starts changing as we move. That third variable changes that according to where we're at along that direction axis. So we're going to talk about surfaces. How many variables do you suppose surfaces are going to have? Because we change in all three directions. That's what goes on here. I'm going to show you how to do them. We still involve traces. It's a little more intense because there's not just one thing. This is literally one thing. Two variable cylinder, draw some parallel lines. This is a little more because we have these extension concepts of the conic sections. So instead of like an ellipse, we have ellipsoids. Think ellipse in 3D. Instead of hyperbolas, we have hyperbolic paraboloids. Think a saddle, like how a saddle looks. That's what these things are going to look like. So I'll show you how to do it. We'll do one example for every type of surface that we need to cover. I got to tell you, later on, we're going to get back to general surfaces with some of our vector functions and the next section. So right now it's pretty advanced, but you can consider this to be an introduction. These are the ones that you can graph by hand. Some of the other ones you can't. You just can't graph it by hand. That's why we've got computers and stuff. All right. So I'm going to show you all the surfaces that we can graph by hand and exactly how to tell what they are. You ready for it? Are you sure you understand this junk?
Yes. Yeah.
That's not very convincing. You're like, I don't want the test to tell. I want you to tell me now. Are there any questions that you have on it? The only reason I liked Calc 3 when I took it was for the pretty pictures. Hope they're good enough for you to enjoy those at least. So I liked them. So surfaces, introduction to surfaces. Well, surfaces are taking the idea of a cylinder and saying, hey, you know that one variable that was missing that said I can't change along the axis, that said I'm directed along the axis? Now take that variable and let it change. Let it change the shape at the points along that axis. That's going to give us these things called surfaces, not just cylinders. So the main things that we have, number one, these all have three variables to them. So surfaces have three variables. Number two, most of them are still going to have a trace on a coordinate plane. I'll show you how to find it. But they also have more trace. I want you to think of the logic here, okay? With cylinders, it's enough to get one picture. Why? Does it change? So the picture doesn't change.
No.
With surfaces, it's not enough to get one picture. Why? So we're going to find traces at least 3 different spots. We're going to find them hopefully on a coordinate plane or on planes parallel to coordinate planes. So you get the idea of what I'm talking about. If one doesn't happen on a coordinate plane, or even if it does, I also want to know what happens later. Does it get bigger? Does it get smaller? How does it change? So we're going to have these traces at a few different spots. So we're going to have traces, but they occur on coordinate planes or on planes parallel to coordinate planes. They're still directed, most of them, all but one, are still directed along an axis, and I'll show you how to identify that. Just keep in mind that the shape is going to change along the axis. And I'm going to say it again. Right now, like when you go home and you watch this again, and you're like, man, I'm really not getting the conic sections. Stop what you're doing and watch chapter 11 where I talk about shifting, and watch chapter 13 where I talk about conic sections. And if you're like, I don't get conic sections, just stop, go to those videos and watch them. Because that, if you know conic sections, honestly, those are really easy. I'm going to show you how to do everything else. I'm not even kidding. They're not that hard if you know conic sections. If you do not, well, if you don't know them, they're going to be impossible. All right, so that's a big deal. So here's our steps. They're the same as cylinders. I'm not even, I guess I'm rounding down. Our steps are this. Firstly, we're going to determine what type of surface we have. I'm going to give you the formula, so you're going to be able to do that. So determine the type of surface. Number 2, once you determine the type of surface, determine the direction axis. Number 3, find some traces. Find a trace on the coordinate plane if you can. And here's an important one. We just talked about it. One trace does not cut it. These are not cylinders. So after you find a trace on the coordinate plane, find at least 2 other traces along that direction axis. Tell you what, let's go ahead and take our break right now, and when we come back, we're going to get through like all of our surfaces pretty much as fast as we can. All right, so we're on to surfaces like in general. Introduction, we got our 6 shapes that we're going to cover for here. They're all based on just some conic sections, circles, ellipses, hyperbolas, parabolas, stuff like that. So what I'm going to do for each shape, I'm going to give you the formula, how they look in general. I'm going to tell you how to tell when we have an ellipsoid, when we have all the other shapes, and I'm going to give you some special notes. So number one, when you have ellipsoid, here's how to tell that you actually have that. First thing, everything is positive. Everything you see is positive. There's no minuses, there's no negatives. Number two, everything has a power 2. X squared, y squared, z squared. And number three, there's a constant associated with it. The constant right here is 1, but before you get it into standard form or general form, it doesn't have to be 1. But what I need you to know is there is a constant. There's something added or that you can solve over on one side, leave it as a constant. The reason why I'm being very specific is when we start changing this, we change shapes. When we start changing this, we change shapes. When we start changing the next one, it has a constant, we change the shape. So these things are all important. So all positive, all power 2, and it has a constant. By the way, under the notes, a couple things. It's not always necessary to solve it for this form. This is called the standard form, but it certainly helps with the pictures of your traces. So it's not always necessary, maybe you'll write a little note there, not always necessary to solve for standard form, but it helps with traces. And the last thing before we try our example, ellipsoids are basically an ellipse in 3D, which means that we can easily find our intercepts. Really, really, really easily find our intercepts. For instance, if we have that, that's a cylinder. And that right there has intercepts at positive and negative A, positive, negative B. That's a cylinder. Intercepts positive, negative A and C. Cylinder intercepts positive and negative B and C. Those intercepts still work. So the intercepts are really easy to find in standard form. Furthermore, if you really think about it, if I let z equals 0, do you see that that gives me a trace of an ellipse on the xy plane, just like this? And if I let y equals 0, that gives me a trace of an ellipse on the xz plane. And if I let x equals 0, that's on the yz plane. That's where we're getting these intercepts from. It's the same idea. Now we're going to practice just one example. They're going to be pretty fast. I just want to verify that all of this stuff works. So I'm going to have always our shape here, and we're going to do our example right here. You guys are right on that one? So we're going to go back and forth. So here we go. Probably one of the most important things you can do is just identify the surface. Just be able to identify it, man. That's important. So, number one, is that a cylinder? How about is that a cylinder? Yes, no. What do you think?
No.
Why not? That's right. As soon as we see 3 variables, then we got
A surface.
we got surface. All right. What type of a surface is it? That's when we check this stuff. Okay, well, let's see. Do we have all pluses like everywhere?
Yes.
Do we have all squares?
Yes.
And do we have a constant?
Yes.
That right there tells us the type of surface we got. What type of, and we only got one to choose from, I know, but what type of surface do we have?
Ellipsoid.
Perfect. So I know it's an ellipsoid. Remember how we write down everything that we know? Please still do that. Please still do that. So I know that everything, it's all plus, all positive. Looking good. It's all squared. Power 2. And with that constant, that is what's giving us the ellipsoid. You know, it's not ultra necessary to do, but it really helps if you put this in the standard form. Because when we cover up those, make the variable 0, it gives us those traces of ellipses on the coordinate planes that we really want. So how would y'all put this in standard form? What would you do?
Divide by 36.
Let's try that right now. Tell you what, I'll take care of this one for you. You're welcome. Z squared, 36, boom. Simplify the other fractions, though. Make sure you do that, okay? We do want something nice. Generally, I'm going to give you nice things. We don't have to get something nice, though. If we get stuff like 13s down here, that's okay. It just means that your graphing, your intercepts are going to be like square root of 13. It's not fun, but it's still possible. So don't give up on it if you get some weird numbers. What goes here?
Square.
Over?
4.
More square.
Over.
Beautiful. From there, can you write out what my intercepts are? Go ahead and take some time to do that. I'm going to do it on the board while you guys do it. How we find the intercepts, it's always below, the intercept of the axis is always below that particular variable, right below it, and we just take a square root. These are just a little bit more involved than...
It's a start. We got it pushed out for you. So.
Thank you so much. So these are a little bit more involved than cylinders in that they change, but if you know how to draw the traces, you can be fine. How many traces did I say you actually need? At least 3. 1 for coordinate plane, and then 2 other ones. We're going to get 3 on coordinate planes. So let's draw them. Just keep in mind what we're doing. Ellipsoid has 3 ellipses put together to make this 3D sphere. So all we really need to do is mark up our axes with the appropriate intercept. So x, positive, negative 2. Y, positive, negative 3. And z, we get positive, negative 6. So when we're graphing them, look, graphing by hand is not the easiest thing to do, okay? And my graphs aren't going to look that great either. The idea, though, is make every sort of ellipse that you can, and then it usually works out okay. So I'm going to start with the ellipse on the xy plane. Then I'm going to start, or continue, with the ellipse on the xz plane. What's the only other one that I have to do? I got the x, y, I got the xz, I need the yz, the one right on the board. It's not perfect, but it's a pretty decent idea of what that ellipsoid actually looks like. Kind of like a football. It's just like a football. Speaking of Super Bowl, that's this weekend, right? Isn't that like a game or something with like these people tackle and things? I don't know. It's coming up, so enjoy that. You better be here on freaking Tuesday and not be all hungover, so. All right. It's got Monday for that, I guess. Yeah, kill brain cells. It's all good for you. You don't need them. It's just math. Anyway, show of hands feel okay with that idea. That's ellipsoids. If I give you one on a test, can you draw it? Is it super hard? No, just follow the directions, man. 3 variables. Yep. Here's the form. Okay, all positive, all squared, has a constant. Get it in standard form, get your intercepts. You're good to go. Let's move on to the next one. The next shape we have. Listen, I'm going to do this to you. I'm going to leave these things up here and just change the pieces that change so that you will be aware of what the formula differences actually are. Does that make sense to you? So we're going to talk about these things called one-sheet, say that appropriately, okay? One-sheet hyperboloids. Like, I don't get a sheet. You're gonna want to know. Sheet. Oh, sheet. Yeah, one of them. What'd the ghost say on Halloween when he got scared?
Oh, shoot.
Oh, sheet. I just made that up right now. Enjoy that. It's not a while to Halloween, but you can use that. Enjoy. So what's one sheet mean? One sheet means that this figure would take one sheet, continuous sheet of wrapping paper to cover it. You could enclose it with one sheet. A 2 sheet, which we will have, would take 2 independent pieces of wrapping paper. I mean, they're not separated. They're not. It's not contained in one piece. You would need 2 different pieces to do that. So this should be one solid thing. Here's the only difference between ellipsoids and one-sheet hyperboloids. Watch carefully. As soon as we start changing stuff about this, we start getting different shapes. That right there is a one-sheet, and I'm giving you a general idea here, okay? That's a one-sheet hyperboloid, but here's the deal. Are they still all power 2? Do they still have a constant?
Yes.
Are they still all plus?
No.
Has 1 minus. That's important because if I change 2 minuses, guess what? 2 sheets.
Does it matter where the negative phenotype
It does matter. And I'm going to tell you that right now. I'm telling you this in general because it's not always going to be this one that's minus or this one. But where the minus is tells you what axis you are directed along. I'm not finished with the notes yet, okay? So I'm going to talk about all this stuff.
So we only need one constant?
This would be the constant. You can only have one because all constants would be combined. Okay, so I'm talking about that as my... These don't really count. Those are coefficients.
Okay, okay, thank you.
All right, so our intercepts aren't really going to work for us right now. We have a different shape, so I'm going to erase this. Again, standard form helps with the traces, but here's the main notes for this. Number 1, the hyperboloid, one-sheet hyperboloid, always travels along the axis with the negative, or minus, if you want to think about it that way. Hey, how many traces are we going to need? What do you think?
3.
A minimum of 3. 3 is good enough, typically. Here's what to do in this particular case. You know the variable with the negative in front, or the minus in front of it, the one that is directed along, that's the important one. Take that variable, take the one with the negative, I'm going to call it the negative variable, take the negative variable, set it equal to 0, and set it equal to the square root of the denominator. And that will give you, plus or minus, and that will give you 3 traces. One at 0, one at positive, the square root of the denominator, and one at negative, the square root of the denominator. And what we're going to get is this nice symmetrical hourglass sort of shape out of it. That's the best way to graph these without a computer. So, here's the beautiful thing. These traces will always be circles or ellipses. Let's try one. Come on, we're going to move quick, but I do want to move quick, but I also want your participation. Tell me everything you know about this.
3 variables.
3 variables, very good. What's that mean?
Circles.
I'm not going to write that particularly down, but so 3 variables. Tell me about those variables. What do you see about the variables? One of them's negative, and they're all squared. 1 negative. 3 variables. Is there a constant?
Yes.
Those combination of those 3 ideas, all squared. One of them's negative, and you have a constant. That tells you 1 sheet hyperboloid. Can you please go ahead? I'm going to give about 10 seconds. Can you get that into standard form? Well, while it's not super necessary, it really helps with the traces, so let's do that. Right setters, you tell me, what's the standard form when you put this into that format? What do you get, please? Uh-huh.
Minus y squared.
Yeah, you know what I also want? I want the variables in order. That's going to make it nice too. So I want to do x squared, and I want to do then y squared, and then I want to do z squared, and then the constant. Okay, that's what I want. It's going to help you. So what's the next thing again?
Minus y squared over 9.
Over what?
9.
And?
Plus z squared over 4. Equals 4.
Beautiful. That's exactly right. That's the first step. You're halfway there, practically. Now, let's write a couple things down. At least one thing down. What axis does this 1 sheet hyperboloid travel along?
Y.
Yes, this goes along the y. Why does it go along the y-axis?
It's the negative variable.
Now, this is pretty confusing to a lot of people. Like, what are you talking about, traces? What do you mean, man? That direction axis, the one that's directed along this thing, that's an important one. And if we start setting that variable, that y variable equal to numbers, I want you to look at this. Stop what you're doing. Look at this. Watch. If I start covering this up, what shape is that? Circle or ellipses. There's circles or ellipses. That's why that statement's there. If I start plugging numbers into this, I get hyperboloids. Do you want to graph hyperboloids or circles? I want to graph circles. So we're going to start plugging numbers into this. and getting circles out of it. Because when I plug in numbers, I'm going to get constant. I can add constants and then divide by that new number. It's going to give me circles and ellipses. Does it make sense? Okay, so we always start off with 0 if we can. So let's plug in 0. If we plug in 0 for our y, it eliminates that whole term. Bless you. Let's define that. What is that thing?
Circle.
Circle. Everybody, what's the radius?
2.
Beautiful. Love a radius of 2. Or an ellipse with a going out 2 in each direction. Still technically a circle. Centered where? Come on, centered where?
0,
At the origin on what plane?
XC.
XC. So we could graph that right now. So we knew circle. At 0, 0, 0, didn't really matter on the plane, with a radius of 2. Something about like that. Sorry, that's kind of ugly. My bad. Do you see the circle I'm trying to draw, though? For a cylinder, that's good enough. Project it. For surfaces, it's not good enough. Here's the most difficult part. This is where I kind of lose people, okay? Here's the most difficult part. The other two traces. What you need to do is plug in some numbers here that make this really nice to add, not fractions. Please, not fractions. Stuff like the square root of that number. Because if I square root this number and square it, it's going to give me 1. I add the 1, I divide by 2. Does that make sense? In this case, we'd be adding, or we'd be plugging in 3 and negative 3. The square root is positive negative. Does that make sense to you? We're going to plug in both. Now, it's going to give me the same thing, but it's also going to give me 2 traces at the same time. This is the rough one. This is the one that people, what are you talking about? So focus here for a while, all right? If we plug in y equals plus or minus 3, what does that become when I plug in, I don't even care, positive or negative? How much does that become?
1.
9 over 9, 1, whatever. I'll put 9 over 9 just so you see it. Head nod if you're with me. Are you feeling okay with that one? Yes, no. Yes, 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 yes. Okay. Now that counts as a constant. Please listen. Constants go here. They get combined, and then we make them 1 again by division. So if I add this 1, we get 2. Guys see where the 2's coming from? This isn't so bueno. Because in order to figure out what the radius of the circle is, I got to have some numbers down here and a 1 right there. So if you ever have this, and you will a lot, just divide this number on both sides. And what that means is take this number, multiply both of those by 2. Dividing fractions right here is multiplying denominators. So if I do this, oops. We get that. I need to understand if you can make it down. You should be able to, but can you make it down here algebraically? Show of hands if you can. Okay, now, please watch carefully. I don't want to have to do this every single time. We're going to be moving quicker after this. What is that?
Circle.
What's the radius?
Square root.
Square root of 8, so like 2 root 2. Square root of 8, how much is that on a calculator? About how much, like 2.8 or something?
2.8.
Is it? Check it out, let me double check because my head sometimes doesn't work that well for stuff like
Square
that.
root of 9 is 30.
Probably 2.8. Somewhere around there. Just double check. Yes, no? Perfect. That's close enough for me. I work for the government. Close enough for government work. So here is the issue that you will make mistakes on. You're not even watching. You get this circle, right? It's on the XZ plane because I put Y to 0. This circle, it can't be on the XZ plane. Why? Because of the Y. Where is that at? It's on a plane that's parallel to the YZ plane, but pushed out 3 spots. And the same circle, parallel, pushed out -3 spots. That's where this circle takes place. It's still centered at 0, 0, but 0, 0, 0, 3, 0, or 0, -3, 0. That's where it's at now. Does that make sense to you? It's a weird concept. Here's the best way I've ever found to do this. When you're graphing these, go to 1, 2, 3. -3. And right there, at those points, you see where the points are coming from, I hope, 3 and -3. Right there at that point, redraw the other 2 axes that you need. That's the best way that I have, because otherwise you're like, where is it going? I don't know. Watch. Just kidding. May as well just do it right? That's like a shifting over the z-axis. Don't do this. This is not the x-axis. That looks like the x-axis. That's a shifting over of the x and the z-axes. Are you getting what I'm talking about? Draw your circle there. At y equals 3, draw that circle. That's what I want you to do. A lot of people get confused because it's hard to do this along the x-axis when you don't know what's going on. Draw the x-axis. It's hard to do this along the z-axis when you don't know what's going on. Draw the z-axis. It works especially well for the z. Especially well. So, what are we going to draw here? At y equals 3, what are we going to draw?
Circle.
What type of a radius? What's the radius there? Pretty close to 3. So if I go, hey, make the same scale though. That's important. I'm going to go pretty darn close to -3. Pretty darn close to +3. Keeping the same scale here, that's important. Pretty close to +3. Pretty close to -3. Do you see how what's happening along, watch carefully, along the y-axis, my circle is gradually growing. That is what's happening. That's all that's happening. And it's gradually going this way. I know it takes a while to do by hand. The reason why you don't have computers, right? That you just do this on your paper. So I want to show you how to draw them with paper so you actually give me something relevant and on test. I could just pull them up on the computer now because they just installed that software. That's what the guy was doing. What? I said, I want software. Done. Thank you. I finally got it. So I'm going to show you in a little while with some software what some of these things look like. But you can't do that. So this is how to draw them as best as possible using paper and stuff. And then draw the circle. So do you know how to get the 2.8, 2.8, 2. Do you know how to get those circles at those spots? Well, draw it. Those things that we just drew are called traces. You need at least 3 of them to do a good job. We typically like one on a coordinate plane, and then the other ones will always be parallel to a coordinate plane. How do we get this one? Set the negative variable equal to 0, gives us a picture of a circle. Right there, at y equals 0. Go along the direction axis, still the negative one. Plug in some reasonable numbers. Typically square root of that number plus and minus gives you 2 other traces. At y equals 3, at y equals negative 3, and when we plug it in, do a little math magic, and then we get another circle, it's just bigger. Make sure these things change. They are not cylinders. And then we just have to do this. Make a nice, we talked about hyperboloids, right? Just bear with me. Bear with me. Ready? Hyperboloid. Hyperboloid. Draw yourself a hyperboloid looking thing that connects the dots. That's what this looks like. If you know conic sections, it's pretty easy. But that's what the one-sheet hyperboloid looks like. We just use circles to draw it because it's easy. Am I making this make sense to y'all? What's next? Yeah. What's next? Let's go home. No, we can't. Like an hour and a half still. No, we're not going to. Listen. Here's what changes between a one-sheet hyperboloid and a two-sheet hyperboloid. You're still going to have all power 2. You are still going to have a constant. The only thing that changes is you gain an additional negative. So here's what I'm going to put. It has 1 plus. It has 1 plus. 2 minuses, 1 plus. Again, standard form helps the traces. Again, it's always, junk. It's always directed along the axis with the minus. How many axes have minuses now? That's a problem. That can't work. So let's change it. What do you think it's going to be directed along? It's always like the odd man out, which is kind of nice. This is going to change a lot, this part. And I want to show you why. Emphasis. Boom. Here's the why. Here comes the boom. Hey, if I set the plus variable to 0, check that out mathematically. Just consider it for a second. I get a negative minus a positive. Can that ever equal positive 1? Doesn't even exist. That doesn't even happen. You can't even do that. So setting the positive variable equal to 0 does nothing. Do not set this equal to 0. What does help is this. Set both of the minus variables equal to 0. And if you do that, check this out. If I set these both equal to 0, then I get the crossing of this two-sheet hyperbola along the direction axis. This thing's going to be directed along the plus axis. It's going to touch that axis. Where? When these two things equal 0. So set both of these equal to 0 and solve for z, and you will find out the z, or the plus axis. You will find out the intercepts of that axis. So I'm going to write that down, and we're going to actually do it in a second. Now here's the issue. This gives us no traces at all. Well, technically it does. It gives us the non-ellipse. It gives us a point. It gives us a little point. So that's good enough to start though. Okay, that's okay. We just need 2 more traces. To find those other 2 traces, remember we need 3 traces, right? Intercepts count as 1. Okay, that's fine. The other 2 traces, take the plus variable and set it equal to some numbers that are divisible by the denominator. So you want to get a whole number out of this thing. And so I'm going to say, because the numbers can change, set the plus variable equal to some numbers divisible by the denominator. It's best if we try one. Man, this is a good example for a test. Just saying. Because it's not really totally apparent what's going on. So you go, all right, what do we have? Write down everything you know. What do you know? Or not write down, at least think it through. What do you have? Do you have all squares?
Yes.
Do you have a constant?
Yes.
Okay. Does it look anything like what we want it to look like?
No.
Let's start solving that. Okay, what would you do here? Okay, move the what first?
No, constant. The constant.
Probably the constant, yeah. And then I would reorder my variables. Oh, but what's it gonna be?
No.
Told you, it's not super necessary, but standard form really helps. What number do I want right there? Positive 1. Notice what's going to happen. Notice, if you try to tell me what's going on right now, you are going to tell me a one-sheet hyperboloid if you do not take that into account. Does that make sense? Get it to standard form, you never make that mistake. So let's divide by the -9, and we're going to change all of our signs. Now when it starts looking like the standard form for something, now we write stuff down. So now it's all squareds. Now it's 1 plus. Now it has a constant. That right there says, huh? 2 sheet. 1 negative, 1 sheet. 2 negatives, 2 sheet with a constant. That's how I always tell. Now let's talk about a couple other things. What axis is this 2 sheet hyperboloid? You don't even know what they look like. We're kind of inventing this as we go. What axis should this be traveling along? The x, the y, or the z?
Y.
So let's double check. It's got 1 plus. Yep, 1 plus. All power 2, we got it. Has a constant, yes, and we're traveling along the plus axis. We're traveling along the y-axis. In this case, you'll be okay with that one. Now, we are only going to get 2 real traces out of this because our first trace gives us intercepts. We treat it like a circle with, or an ellipse with 0 real dimension. It's an intercept, though, and that's what's going to give us. How to find that? How to find that? Set both of your negative variables, set them both equal to 0. Set them both equal to 0. And what that does, it has to give you something on the intercept of the y-axis. It has to give you something on the alternate axis. If you set both the other variables to 0, you're on an axis. What variables should we set equal to 0, folks?
X and Z.
Hey, if you set x and z equal to 0, you get y squared over 9 equals 1. Super hard? Not really. What's y going to be?
Plus or minus.
That's it. Just don't forget the plus or minus, because we have 2 sheets, 2 sheet hyperboloid that go in opposite directions. So here's what I know. I'm going to draw the first little piece of it. Oh. I know that because I'm limiting my z to 0 and my x to 0, I have to be on the y. Where am I on the y? Where am I crossing? Here. At positive negative 3. At positive negative 3. Sorry I'm writing small, but this graph's going to get a lot bigger here real quick. Now, the other ones for the traces. It's still going to be plus or minus, but I want to plug in a number that when I square it is going to be divisible by 9. That's what I want. Why? Because I want this to be a nice number. I don't want fractions. I want to be able to subtract it and then change my signs. That's what I want. What number should I use?
3.
If I plug in 3, I'm going to get 0. Why? Because we literally just solved for that value of y. You guys see what I'm talking about? You can't pick these numbers. Those intercepts are going to give you 0. That's the only problem. So what do you pick? You be smart. There's no other way for me to tell you, but think about it. I would pick something like 6. I'd pick something with a 3 in it. Because when you square it, 9, when you square that, you're going to get a 9 squared. It'll be divisible by 9. I would pick 6. That's the smallest number that we can square, and it's divisible by 9. So I would do that. Did that logic make sense to you? I know that it's kind of weird, right? Because you have to really think about it. But pick 6. That way you're finding something that when you square it, you can divide by the denominator. So when we pick that, hey, plug it in. Whether you pick positive or negative, you're still getting 36. This is going to happen every time. Every time. You're going to get negatives everywhere. What do you do when you get negatives everywhere? Change all your signs. And then one last thing. Oh, one last thing. I don't like that number. How would you get rid of that number?
Divide by 3.
Am I losing you guys?
No.
I don't want to lose you. How do you get rid of that number?
Divide by 3.
Dividing everything by 3 is multiplying the denominators by 3. I didn't promise it was going to be nice. I just promised you were going to know how to do it. Let's see. What shape is that? Come on, what shape is that?
Ellipse.
That's right. Parallel to the XZ plane, but not on the XZ plane. If you can answer this, I'm going to be happy. Happy, happy, happy. Don't get it wrong, because then I'm going to get mad. You're a monster. Okay, don't do that. That's pretty close. Where does this ellipse that has a rate, well, x goes along square root of 27, z goes along square root of 3. Where does that occur? At y equals what value? So whatever you plug in, go to that value, redraw the other two axes. I know it's time intensive. I really do apologize for that, but if you're going to do it right, it takes some time. It's some pretty cool looking graphs though. Hey, can someone tell me, this x, what's the square root of 27 about? I know that's exact, 3 root 3. I mean about, so I can actually do it on here. Come on. How much? Square root of 27 equals 9? About 9? 9.5? 5. Okay, so about 5. Let's go to about 5, a little past 5. Are you seeing what I'm talking? I don't want to have to repeat all of this stuff, but check it out. Hey, set both these equals 0, you get your y-intercepts. We're right there. Find a good number, a number that the denominator divides when you square it. Subtract it, change your signs, divide it. We now have an ellipse that's taking place at y equals negative 6 and at y equals 6. It's going to be an ellipse, and it's going to be an ellipse. The x spreads out about 5.1, plus and minus. Square root of 27, about 5.1. Does that make sense? The z, how much is the z spread out? About 1.7, square root of 3. So on my z-axes that I shifted over, we're about right there. And we're just sketching, but having an idea is really nice of what it looks like. On the x, square root of 3, up and down. Square root of 27, that's about 5.1. 1, 2, 3, 4, 5 point. Pretty close. 1, 2, 3, 5, pretty close. 1, 2, 3, 4, 5, pretty close. 1, 2, 3, 5, pretty close. Do you see how redrawing the x-axis and redrawing the z-axis is going to make your lives a lot easier? Trust me on that. That is the best way to go. All right. Otherwise, you're like, I don't know. It's really hard to tell. And you get some really crappy looking graphs. They're already going to be crappy. Okay, we're not great at this by hand, but don't make it worse by not doing that. So from here, here's the cool part about it though. the cool part about this is that if I can draw this ellipse, which I know is taking place at x equals 6, it's going to be hard because it's pretty extended here. And this one. And here's what happens. We connect this. Kind of mess it up. Basically connect the dots. Sorry, it's not better. Can you see the picture I'm trying to present to you? The picture is, this one's a little off. The picture is these bowl shape, almost parabolas, that are coming out this way and coming out that way. There's nothing between them. That's why we call it two sheets. If you were to wrap these presents, you would need 2 sheets of wrapping paper to cover those things. That's why we call it 2 sheets. The other one was 1 sheet. You wrap it all with one shape. Do you guys get the picture? Yes, no?
Yes.
Maybe so?
Yes.
Are you sure?
Yes.
Could you do it?
Yes.
Do you have any questions about it? Could you at least tell the type of shape it is by looking at the formula and going, oh yeah, okay, hey, constant, all squared, 1 plus, 2-sheet hyperboloid along the y-axis. Do you know why in the world I'm plugging in 6 and negative 6? Do you know? Why?
Well, it's a number you can square. It's divisible by 9.
That's the one. And then that's going to give us these nice ellipses at these values of on the direction axis that we just plugged in. For real, show hands feel okay with that one. Okay, we got a couple more. A couple, 3 actually. So we're going to talk about cones. I think we're going to take our break after that, and then we'll come back and finish up paraboloids and hyperbolic paraboloids, which are super fun. Awesome. So let's talk about cones, and we'll call it good. Cones. Here's what cones do. Here's the difference between. Let's see if you were paying attention, actually. Cones are easy, by the way. Cones are really nice. I'm going to show you the easy way to do cones. If you know what that is, I'm going to be happy. What is it's not a cone. Okay, it's not a cone. I'm going to change it. What is that?
One shroud.
Beautiful. How do you know?
1 minus.
1 minus.
One
All squared.
and a constant.
Cone. It's the only difference. Do you see why you need to be familiar with these things to get them right? Because if you have the same exact jump, but you don't have that constant, that's now a cone. Here's what's nice about our cones, though. Our cones are always going to be crossing at the origin for us. We're not going to be shifting them around. So I know that these cones, and by the way, cones are a full cone. So up and down. So we're going to have cone and cone. That's what's going to go on here. Here's how to tell. They're still all power 2. We're back to they have 1 minus. The big deal is they have no constant. What's the odd man out? The pluses or the minus? What's the odd man out?
Minus.
It's going to travel along the one with the minus. Is me teaching you this way making sense that you can see the differences between them? The odd man out sort of thing? I think that it is. these all, if you want to write another note that I'm not going to write up here, they all cross at the origin. Again, though, just look at this for a second. Don't write this yet. Don't write this. If I set that equal to 0, what's it tell me? It tells me I'm at the origin. Is it, oh yeah, I have to have zeros here to make that happen. It tells me I'm at the origin. So because neither of them are negative, you can't subtract anything. They're all positive. So this, if I set that equals 0. We're at the origin. That's why I said write down all of these cross at the origin, because you don't ever set this equal 0, because it just shows you that you're at the origin. So if you want this says nothing. Or it says you're at the origin. That's what it really says. So the idea then is, let's plug in some values for the negative variable that again are divisible by the denominator. That's what we want to do. What this is going to give you, if I plug in some numbers here to the negative variable, please look for a second. If I plug in numbers here, it's going to give me a number. It's going to be a minus number, which I will add to the other side. If I add that to the other side, I now have a constant over there, and that gives me circles or ellipses. Do you see it? So plug in some numbers to that variable, add it to the other side, and then we're going to have circles or ellipses. That's why we get a cone. That's why. Tell you what, we're going to burn through one pretty quick. That will leave us with just two. The paraboloids and the hyperbolic paraboloids that we'll cover after. If you look at this on a test, can you tell immediately what that is? How can you tell? It's the first one we have not had a constant, but they're all squares. However, wait a minute. How many minuses are we supposed to have?
One.
There's two. Could you just move them all to the other side, or just change the signs when you have that 0? Just take care of that. So if you have this, oh man, I don't see a constant, so there's no constant. All square, that pretty much looks like a cone to me, except for the fact that this has 1 minus, this has 2. When that happens, you have 0, it's the same thing. Just change all your signs, divide by -1, multiply by -1, add everything to the other side. I don't care how you do it. Just put them in the correct order. We're going to go, okay, let's add this. Let's add this. Let's subtract this. And now we have that. Yeah.
Will there ever be a point where we have two negatives and it will be a different shape?
Two negatives and a different.
Well, would we have original?
So like that one?
Yeah.
You can't. Because it's 0, right? So I mean, it is the same thing as the cone. It's just we have it in that format to make it nice for us, because all this stuff really works pretty well. Does that make sense? You guys okay with that one? Are you sure? You sure you're sure? Okay. I'm fine with it. Now, it doesn't quite look like that. Could you make it look like that? The standard form's pretty nice, right? What would you do?
Divide
You
by
got a 0, right? You can divide that by anything you want except 0. What would you choose to divide by?
36.
I divide by 36. Let's do that. If we divide by 36, that at least looks a little bit better. It's kind of nice. So now we go, okay, yeah, that looks better. There's no constant that all squares, there's one minus. That's for sure a cone. Quickly, where are all cones centered at? For us, yes, that's right, we're not going to be shifting them. If they're all centered at the origin, that acts like one trace. I love that. What axis is this cone, quickly, what axis is this cone directed along?
Z.
Why? How do you know it's directed along the z-axis? The origin acts like a trace, like one trace. It tells us this. That no matter what, I'm crossing there. That's what we're doing. No matter what, I'm crossing there. The other two traces, that's what this stuff is for. Let's plug in some values for the negative variable that are divisible by the variable. Now, here's the nice part about this. You can always use that if you have put it in standard form. That's pretty cool. So what number would we use to plug into the what variable? What variable, what number? Oh, this is lackluster. Goodness gracious. What number are you going to plug stuff, or what variable are you going to plug stuff into? Z, because it's the minus 1. What number would you use? 6. Plus and minus. One trace at the origin. For the other trace, let's do that. If we plug in plus or minus 6, we're going to square it. It's going to be 36. Oh, I got 36. I love that. Also, if you do that, this is beautiful. Because when you add that to both sides, if you pick the correct number, you get 1. And it's already in the form of circles and ellipses. Boom. I love that stuff. You know, you take the time to really make it look nice, and it pays off here. It's like getting up in the morning and brushing your teeth, you know? You don't have to, but darn it, when you're in the math lab and I start talking to you and you're not like, whew, it pays off, you know? It's a little gamey. You can brush your teeth, dude. This is brushing your teeth. This is getting your mathematical hygiene in order so that you're doing good later. So it makes it easy later. So at this x equals plus or minus 6, here's what we do. Cones are pretty easy. Cones go, hey, what value did I just plug in, and what axis did I plug it in at? Or to?
6.
Z, 6. That's the Z. And I just plugged in 6. Now, at 6, plus or minus, what shapes am I getting? Ellipses. Ellipses with the x spread out plus or minus 2, with the y spread out plus or minus 3. Are you following me? What that means is, just like before, wherever you just plugged in your values, go to this axis, go to this number, and right here, redraw the other two axes. This is the first time we've done it with the z. It works really well with the z. All of them, really. So at those values you just plugged in, so z equals negative 6. Redraw an image of the y. Gotta be parallel. We draw an image of an x. Y and x. And then on those images of the axes that we just shifted up, that's all we're doing. We're just shifting this up until we get a good picture. Where are we shifting it? Plus or minus 6 on the z-axis. Where those new images are, a little off here, it'll be fine though. Where those new images are, now draw this shape on this shifted up image of your xy plane. That's what traces do. Just try to keep the same scale. Otherwise it won't look that great. So we're 2 on the x, or the image of the x. We're 3 on the y, or the image of the y. We draw our ellipses. Now here's I'm going to do it logically. I'm not going to prove it, but I'm going to do it logically. What's happening is we start off, and at every number, we would get some ellipses. Do you understand? So these ellipses are just getting bigger and bigger and bigger and bigger. They start out at 0. That's our first trace. It's technically an ellipse with 0 dimension there. So what this is going to do is we're going to create this cone that crosses through the origin. Oh, I did a good job. First time for everything. Actually worked pretty good. It's almost like I know what I'm doing sometimes, you know? Almost. Just pretty. Use this technique. It actually works. That's an image of the cone that we just created. Do you guys see the cone that we're creating? That's the plan, man. We've covered 4. We got a couple other ones. Honestly, the next one is the easiest one that we covered. The paraboloids. I think we need a break though, so we're going to do that, and we'll come back. All right, so welcome back. We got like 2 more shapes. The ones that you probably try to do in your homework, like what's those ones without squares? The last 2. That's those ones without squares. We got 2 more shapes: paraboloids and hyperbolic paraboloids. And you go, all right. What we've been kind of rolling with is, here's the formula, here's how to tell what shape you have, here's some major notes on it, and then I'm going to give you one example. We're going to keep on going with that. So let's look at the formula for paraboloids and see how it differs from practically all the other ones that we have had. Man, you're going to notice something right off the bat. And if you looked at some of those formulas, like on your homework, or you've seen them before, they look completely foreign, like automatically. So if you have, okay, let's recap a little bit. If you have 2 variables, I don't even care what you're doing. If you got 2 variables, what do you have?
Cylinder.
You got, oh come on, one person. What do you got? If you got 2 variables, you got it right. But what do you have if you got 2 variables? You got a cylinder along the axis of the variable that you're not given. Are you following what I'm talking about? If we got 3 variables, we for sure have a surface, so that's going to be a surface. It is a paraboloid, but it looks different from what we've had before. Everything else we've had has had everything being squared. This is the first one we've had that doesn't have that. So if we have 3 variables, and one of them is not squared, we have one of our last 2 shapes. We have a paraboloid or a hyperbolic paraboloid, which we talk about in just a second. So paraboloids look like this. How to tell what they are? 3 variables with 2 squares, that's the first one. Three variables with 2 squares. Also, the variables with the squares have to be positive. They got to have pluses in front of them. That's pretty much it. The third thing I'm going to write down probably goes, probably goes more along with notes. So the notes I want you to know about this is the following. The number one thing that I want you to do is be able to recognize these shapes. That's a pretty big deal. Have it in your head what's going to happen. One way that we do it is by recognizing, hey, all squares, all pluses with a constant, we have an ellipsoid or one of these shapes. With paraboloids, it's important we know there's only two squares. There's three variables, but only two squares. Also, what I want you to see here is that constant, whatever, if there is one, whatever that is going to give you the direction that paraboloid opens in. So if we have a plus, it's going to open towards the positive of this axis. So a few notes here. Paraboloids travel along the axis of the variable with degree 1. So it's always the degree 1 variable, that's the axis that this thing opens along. Is that making sense to you? Are you guys focused in today? Oh, okay. Yeah, still. So, the paraboloid opens along the axis of the variable with degree 1. Little side note. The coefficient of that degree 1 variable is going to tell you how that paraboloid opens, whether it's opening towards the positive axis or the negative axis. Should say it this way: the coefficient of the degree 1 variable gives you direction. A positive coefficient means it's going to open along the positive axis of whatever that variable is. And negative means it open. You can think up and down, but unless we're talking about the z, up and down doesn't really work that well. So I want to talk about opens towards the positive part of that axis or the negative part of that axis. So the negative opens, this paraboloid would open towards the negative part of that axis. And then the last little note. The idea behind this, and hopefully you see it, what's going to be really nice if we have this in this form, you don't have to get it in this form, but what we really want to have happen, we want to be able to plug in 0 here, and if we have a shift, if we do that, if we plug in 0 or a number for the 1 degree variable, if we do that, what we're going to get is some sort of a trace on a plane that's parallel to the two other variables given that are going to be circles or ellipses. That's going to be nice. You guys see that if I have numbers here, that's either a circle or an ellipse. You guys see what I'm talking about? Those are really easy to deal with. So the idea is plug in 0 for your degree 1 variable. If it's shifted, it's going to give you a trace right on the coordinate plane. That's really nice. If it's not shifted, then you have to start plugging in larger numbers, things that give you traces on planes parallel to that one, but maybe a little higher or a little lower. I'm going to give you a nice one to look at. We'll talk about that in a minute because right now it's a little vague. But write this down, then we'll do our example. Set the degree 1 variable equal to 0 to get a trace on a coordinate plane. I'm going to make a little side note. This works only if the paraboloid is shifted. If it's not shifted, then you start plugging in other numbers for that 1 degree variable to get traces on parallel planes with the coordinate plane. A little above or below, we've talked about things like that before, but I want to show you an example. So let's start with this one. Number one thing, you notice something really funky about this one. Compared to everything else that we had before, what's the first thing that stands out to you here? Number one, how many variables do you got?
3.
Okay, but what?
One of them's not squared.
One of them's not squared. Right there, that's none of our previous shapes. So this is a new shape. Remember we're talking about writing down everything? We're writing down everything. So we got 2 squares, we got our 3 variables. Also, we notice one more thing. Are both squares positive? So what we're looking for is we want 3 variables, but we want 2 of them squared, and we want the variable with the squares, they're positive. And that's what we have. So right now, this tells us that we have got paraboloid. Let me ask you a question. What axis will this paraboloid be opening along? What do you think? How can you tell?
It's not squared.
Now, how about this one? Will this be opening towards the positive z or the negative z? What do you think? How can you tell that? Just the coefficient right in front of it. Toward positive z values, toward positive z axis, however, you're opening upward if you want to. I don't really care, as long as we get that picture down in our head. Now we're going to do one more thing here. We're going to check this out. What's that do? That's a shift. If you know anything about graphing functions at all, whenever we have it even looks like a function, right? This is like an f of xy. It is a function. We have talked about functions, but we will. When we have a single variable equal to something else and all the other variables, that's a graph. And when we have at the very end, something minus or plus, that's always a vertical shift or a shift along whatever the axis is, where plus means towards positive and minus means towards negative. So I'll tell you right now, that's a shift down of 4 spots. So here's our z-axis going this way. Whatever's going to happen, this thing is going to be shifted down 2, 3, 4 spots. Show of hands if you understand that. Okay, so that's some basic graphing, but that's important. I want to show you another format that you're going to see it, because right now if you look at it, this isn't anywhere close to that form. All right, and we don't have to put it in exactly that form, but getting close helps. I'm going to show you this. What I'm going to do right now is I'm going to add that 4 over. I'm going to add that 4 over. This is typically how I like to put the formula or the equation for paraboloids. There's only one drawback here. Please listen. Please listen. A lot of people get really confused as to, wait a minute. Wait. That's now a shift up 4. Listen, I can't alter the shift just because I put it in. Get your shift right, all right? I can't alter the shift just because I put it in a different format. I want you to think about it this way. Anytime I ever have a number being added or subtracted right next to a variable, it's a shift, but it's like opposite of what your brain wants to think. So when I have that z plus 4, it is a shift along the z, but it's down 4. It's not up 4. Only when you have one variable solved for that variable do those numbers at the very end go the direction you want them to go. Any other time, it's pretty much backwards. Show of hands if you feel okay with that one. So this right here, that's a shift of 4 towards the negative axis is how I want to say that. You can say down 4, I don't care, but this is shifted. Yeah, we'll say down 4. That's a shift down 4 on the z-axis. Let me test you here real quick. Just a little aside, okay? What if this piece of it, what if this piece would be negative z minus 2? Would that paraboloid, it'd still be along the z-axis, recognize that, yes, no? Would this be opening towards the positive z, or would this be opening towards the negative z? What do you think? It would be opening towards the negative z. That's what it'd be opening this way, for sure. Why? Because that's negative. Even if you distribute it, it's negative. Now here's the next one. Is that a shift up or down? What do you think?
Down.
If I just look at you long enough, you're going to change your answer back and forth?
Down.
Down.
You guys are describing dance moves. I like to dance. Don't make me dance. You don't want to see that. I would have showed you my math moves. Up. It's up. It's opposite of what is next to that z. That's up. You go, wait a minute, what about negative z? That's plus 2 though, Leonard. That's plus, but that's negative. That's negative. It reverses things. So if you were to solve for, if you were to have this, please watch. If you're confused on this, please stop whatever you're doing. Just watch for a second. If you have this, you got to change a whole bunch of signs around, right? You got to change stuff around. Firstly, it probably destroys our shape. But secondly, this becomes, if I solve for z, I'd subtract the 2, but I'd change the sign. That becomes a plus 2. At the very end of the function, that would be shifted up. It destroys our shape. I know that, but I'm talking only about the shifts right now. Are you guys okay talking about the shifts right now? Yes, no? I got to pronounce that word real carefully. Shift. Ha ha ha. That right there would be a shift up 2 spots. When you have a number being added or subtracted next to your variable, it is opposite of what your brain wants to think of it. So here, shift down. Here, shift up. That's the idea. Head nod if you're okay with that one. Now I want to get back to our example. What I told you is that if you have that degree 1 variable set equal to 0 and you have a shift, it's going to give, this is probably our nicest shape. No kidding, it's probably our nicest shape to graph. Because it's going to give you 1 trace, and in this case, 1 trace is enough. Unlike the other ones, 1 trace is enough. So what are we going to set equal to 0, the x, the y, or the z? Set the 1 degree variable equal to 0. Do you see it? Do you see something really nice? Now I hope that you've noticed this. Every other time we had this, we really tried to put things in standard form. Please notice, we didn't do that here. This is one of those times when it's easier not to, because when you plug in 0, you get something that you can divide really easily. That's kind of a nice thing. So when we don't have that shift, yeah, sometimes standard form pretty nice. When we do have the shift, don't put it in standard form. It's hard to cope with that plus 4 when you start dividing stuff away. Does that make sense? So plug in that 0, we go, okay, hey, now we can put standard form. Now we can have stuff like x squared over 4 plus y squared over 1 equals 1. Everyone in class right now, what in the world is that, and where is it located? What is that? That's an ellipse. X gets spread out how much?
2 plus minus 2.
Y gets spread out how much? So along the x-axis, plus 2 minus 2. Along the y-axis, plus 1 minus 1. Where? Okay, if you get it, so happy. Woo! It's like a double whammy. Sneeze and a woo. Where is it?
Z equals 0.
What is z equals 0? What is that? What plane is that? Come on, what plane is that? That's just the xy plane. That's why I said you're going to get it on the coordinate plane. It's really nice with these paraboloids. So when we draw it, I am 1 yardstick short of a meter. Yep. Stole my yardstick. Crack him over Go ahead. Okay, so when we draw this, we notice something, right? Whenever we do these traces, we go wherever we plug this in along whatever axis we're directed along, and we redraw the XY axis. Remember doing that? Except if we're at z equals 0, we literally already have that. Draw this ellipse at that place. That's what makes it nice. So we knew that we were going to go out x equals 2 and negative 2. Y equals 1 and negative 1. Let's draw our ellipse right there. But we also knew something else. We knew that this paraboloid was shifted down 4 on the z-axis. What that does, that gives you a z-intercept. So I know a couple things about it. I know that along the z-axis, I've shifted down or towards the negative 4 spots. I also know something else. Check this out. This is pretty cool. Okay. What axis is this opening along? The z. So that makes sense. We're on the z. Is it opening towards the positive z or the negative z? So I have to intersect here. I also have to open this way. I also have to have that trace, which means that this paraboloid is going to go through here, through here, through here. Oh man, I completely missed. We get that shape, sort of, if you can visualize that. I want to make sure that at least I've explained this well enough. Can you guys visualize the paraboloid? It's a parabola in 3D. That's all it's doing. It's just taken from this negative 4 on the z-axis, opening this nice little vase, opening upwards. Show of hands feel okay with that one. Any comments, questions at all? If I give you that on a test, would you be able to do it? Are you sure? So the idea is, hey, look at your equations, make sure you have 3 variables, only 2 squares. Both squares have to be positive. And then, if you have a shift, just set that, identify the shift, know where you're at on whatever axis. It's always traveling along the axis with the degree 1. Set that equal to 0, and you get some circles or ellipses. It's going to give you a trace on a coordinate plane. Combine that with your shift, and you got this nice, pretty easy picture. You only need 1 trace here. Are you sure you're okay with it? Okay. Now stop. Just real quick. What if that's not there? What if that's not there? Is that shift? Okay, wait. Is it still along the z-axis? Is it still opening towards the positive z-axis?
Yes.
It's going to be this, but it's going to be here. It's not shifted any longer. So, but the problem is that eliminates that trace for us. So when you get something like this, you go, wait a minute. If I plug in 0, verify this. If I plug in 0 for that, there ain't no way that's happening. It literally cannot happen. Because you can't add a positive plus a positive and get 0. It's not happening. So when that happens, pick some logical numbers that you would plug in, like, I don't know, something that's the common denominator of these things, like 4. I'd plug in z equals 4. Do you guys see the point of doing that? You plug in z equals 4, then when you divide by 4, actually, you get the same thing, except for one thing. Please watch carefully. I don't want to blow your minds, okay? That looks exactly the same as what we just had, correct? Except it's now at z equals 4. So what that would do is you come up here, 1, 2, 3, 4, redraw your x, redraw your y, and you'd have your trace right there. It would basically undo the shift that we just talked about. I need to know that I'm making sense, making a whole lot of kind of looks from you guys. Is this making sense to you? So if you have the shift, it's easy. Plug in 0, done. If you don't have a shift, plug in the common denominator of these things, and then when you divide, you at least get a reasonable trace at a reasonable value along that z-axis. For real, show of hands, feel okay with it. Okay, we're going to talk about our last one. Our last one says, you know what's going to happen, right? As soon as we start changing anything about that formula, our shape starts changing. So what I'm going to do, I'm going to do that. It's going to give us an entirely different shape. And what we call this shape is a hyperbolic paraboloid. Here's how you tell. It's got 3 variables. 2 of them are still squared, but 1 square has a minus or a negative. The degree 1 variable still gives us the axis of direction, our directrix, our direction axis, but it works a little funny. So degree 1 variable still gives us the direction of travel, our direction axis. But this stuff's going to change, and the whole, I mean, I could just give you the formula and say this is how you do it, but I want you to understand why. I want you to understand why these shapes are the way they are. So here's what we're going to do. We're going to plug in both positive numbers and negative numbers into the degree 1 variable. Plug in both positive and negative into the degree 1 variable. And for goodness sakes, I want you to see why. I want you to see what happens here. Are you with me? If I plug in a positive number here, so this is positive. I say, hey, positive number. This is just a positive constant which I can divide by. I can do that. What do we get? Those of you who watched conic sections and you know this, x squared minus y squared. What do you get? What is that shape on a plane? What is it? It's a hyperbola. Do you know what hyperbolas look like? Those things that you probably confuse for parabolas, they're not. They do this like that, or they do this like that. They do these 2 things. That's it. How do you know which one it does? This one along the x-axis happens when the x comes first and is positive. So if I plug in positive number, I get hyperbolas along the x-axis. Does that make sense? But wait, if I plug in a negative number, and I divide by a negative, these signs change. Now the y is coming first. Is it still a hyperbola? Yes, but now it's along the y-axis. Isn't that interesting? So we get this shape, depending on whether we plug in positives or negatives, that the hyperbolas switch from doing this x hyperbola to doing a y hyperbola. And we get this really, really unique shape called a hyperbolic paraboloid. So the whole idea, yeah, it's still going to travel along the axis of the degree 1 variable, no problem. How you're going to figure it out, plug in some positive numbers and negative numbers of the same value, typically, and then we're going to get 2 types of hyperbolas, some along the, in this case, x-axis, or in the other case, y-axis. Let me show you an example that's going to really clear things up. Also, just like before, it's not super necessary to put these in standard form right away. It actually works a little bit better if you don't. There's only two examples that work that way. Other ones, man, standard form is so nice. But here, it's kind of nice to deal with it without standard form and just divide a number away, especially if we have stuff that's shifted. It works better. Okay, so your test is coming up, and I give you this problem on the test. My first question is to you, do you even know what it is? Can you identify what that is? True or false? It's a cylinder. That should be like immediate. How do you know when something's a cylinder? Come on, put it all together. How do you know when something's a cylinder? 2. This has 3, not just 2. So it's definitely a surface. What type of surface is it? Well, how many squares does it have?
2.
Okay, 2. And so it's either what one of two shapes? If it's got 3 variables, 2 squares, one of two shapes, what is it? Paraboloid or?
Hyperbolic.
Absolutely. Now, it doesn't look quite good to me. I noticed that on both the paraboloids and the hyperbolic paraboloids, I have my squares on one side and my 1 degree variable on the other side. So when we solve for that, we go, okay, hey, it was one of the two shapes. Now we know what it is. Tell me everything you know about this. What do you see about it? It's got how many squares? 2 squares.
Negative.
1 negative.
Opens along the Z.
What is it?
Upward.
How do we know? Sorry, how do we know what shape is it? Is what I'm asking you. What shape is it?
Hyperbolic.
What differentiates a hyperbolic paraboloid from just a regular paraboloid? What separates that? Good, perfect. So if that was a plus, we'd have another paraboloid. Since that's a minus, we have one of these negative. We know that this is a hyperbolic paraboloid. Everyone in class right now along what axis? Come on.
Z.
Boom. Along Z. Now, I can't tell you, or I can't ask you, how's it open? What is it open along? That's not what this is all about. You see, what's going to happen with all of these hyperbolic paraboloids is that all that's going to happen is that the positive values of Z and the negative value, you can see it. Plug in positive numbers. Please visualize. Just try to visualize. Here's your XY, right? Here it is. And your Z's doing this. If I plug in positive Z's, positive numbers up here, I'm going to get hyperbolas that are parallel to the XY plane. Do you guys see what I'm talking about? They're going to stack, but they're going to be traveling along the x-axis. This way and back this way. Do you guys see what I'm talking about? As soon as I plug in negative Z, I have to divide by a negative to get that standard form for hyperbolates. It's going to switch it around to be y squared minus x squared. So above the xy plane, I get hyperbolas along the x-axis. But below, since my sign changed, I get hyperbolas along the y-axis. You guys see what I'm talking about? That's going to create a really weird shape. I'm going to show you this in just a minute. I can't draw it by hand, but I'll show you how to do it. Got a computer program. I got one. They finally gave me a computer that works. It's sweet. 12 years, finally got a computer that works. I love that. That's how long you got to put in hard work, folks. 12 years. Then you get a computer. Sweet. It's like tenure or something like that. Hey, what values would you use here for Z? What do you want to use? Plug in something you can divide nicely and get something nice. I would pick like 1. So let's use our 1 degree variable equal to positive 1 and negative 1. Use the same value, but you have to put a positive and negative because you're going to see what the hyperbolas are doing, where they change. So if I set Z equal to 1, I get x squared minus y squared equals 1. We've already talked about it. I'm going to go through it pretty quick, all right? These are hyperbolas on the Z equals 1 plane. So So they look just like they're on the xy plane, but shifted up one whole plane to z equals 1. So at z equals 1, we get hyperbola. Along, those of you who know conic sections real well, hyperbola is along what direction, x or y? But if we plug in -1, in order to get that standard form, you have to divide by a negative. If I do that, this sign changes, that sign changes, and we get y squared minus x squared equals 1. So at z equals -1, down here, my hyperbolas change. Now I have hyperbolas, but they're along the y-axis. This is the last chance that we get to do this for a while, to draw one of these shapes, so I really want to make sure it sinks in. I know it's been a little while since we did this. Who needs a ruler? Come on. I hope, for goodness sakes, that you remember this. Whatever variable you're plugging a number in for, it creates a trace at that plane. So if I plugged in z equals 1, what's going to happen? I'm going to get hyperbolas, but it's going to happen at z equals 1. Let's pretend that's z equals 1. Do you remember talking about this from last time? From last time we go, okay, wherever you're plugging in, redraw whatever other axes you're not plugging numbers in for. So I would redraw parallels of the x and y. And at z equals -1, I'm going to redraw parallels of the x and the y. Can you guys see what I'm trying to create? It was the idea of those traces. You remember the traces? You go, hey, you're plugging numbers in, right? Where those numbers you're plugging in, those are along an axis. At that axis, you're going to create a trace on a plane that's level to a coordinate plane. So in our case, we have this at, hey, really level to x and y, but just shifted up at z equals 1. Right there, when we redraw the x and the y, we can draw hyperbola, this hyperbola, at z equals 1. And you already told me, but tell me again, what axis are these hyperbolas opening along, the x or the y? It's always the first variable. Which one is it? So this is going to look something like this. Hyperbolas coming out like that. But down here, at z equals -1, those hyperbolas switch now. They're the same looking stuff, but now they're going along what axis? Come on, quickly, what axis? So they're going to be going this way. I know that doesn't look so pretty. Some of you guys are falling asleep with your eyes open. Goodness gracious. Am I boring? I hope I'm not boring you. I am, apparently. Goodness. I didn't think it was that boring. I could make it worse. I really could. I'm not gonna, though. Somehow we have to connect this. We got to connect this thing. So these hyperbolas are like going this way and this way. And how in the world does that look? Can you get the lights for me over there? Better adjust this here real quick. That's not going to be the best, but it's the best I can do. Are those all the lights? Right, so can you see that picture okay for you guys? This right here is a hyperbolic paraboloid. I'm going to show you a few things about it. Firstly, it's kind of pretty shaped. They call it a saddle. It's like a saddle graph because it looks like a freaking saddle. Okay, that's why they call it a saddle graph. Hello. But check this out. I want you to see some cool stuff about it. If I do what are called contours, these are level curves. Oh my goodness, what shapes are those?
Hyperboloids.
Notice how above the xy plane up here in this region, they are traveling along the x-axis. And below the xy plane, they're traveling along the the y-axis. Do you guys see what I'm talking about? That's pretty cool. Right now, I'm going to say a couple things about this. This is called a contour plot. We get a lot of contour plots in this class. What a contour plot does is it looks from above and creates like a topograph. Do you ever heard of a topographical graph? It says, hey, here's your levels, and it just puts them on a map, like flat. That's what this is doing. All these things are traces of hyperbolas that are surfaced together, and we get this really cool looking graph out of it. You guys understand the idea of a hyperbolic paraboloid? As soon as you start changing numbers up here, like put in 4y squared, it's going to start changing the nature, the flex of that saddle. If you want to see the last graph last shape we graphed, that's this one. This right here is a basic paraboloid. That's all it is. It's this parabola that's basically in 3D. If you want to see the contours of it, those are those ellipses that we just drew. Do you guys see what I'm talking about? It's pretty neat. And from the side, it would take parabolas to match this up. To go along the edges of those ellipses, it takes parabolas. That's why they call it a paraboloid and a hyperbolic paraboloid. Is this making sense to you? Do you guys like seeing these pictures like that? Can you visualize it a little bit better now?
Yeah.
That's what they're doing. Obviously, I can't I can't draw them like that, man. I'm only human. The light's working. Oops. I mean, really, mine's just as good when you think about it. So, no big deal. But that shape that we just saw, that's really what this one is. And I hope that you saw the contours, you saw the really why it is the way it is. Show of hands if you did, if you feel okay with that one. So if I give you a cylinder, or I give you a surface, can you right now identify the main things about it? Firstly, what shape it is. Secondly, what axis it's traveling along. And thirdly, can you give me at least 3 traces? Yes or no? Okay, we're going to pause right there.